Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the Sp3 hybridization with one lone pair in the structure. In the previous lecture, we have also done again the Sp3 hybridization, but in that case we were having all the bond pairs but not the lone pairs. So today we are going to take an example in which there is one lone pair in the main structure. So let's take an example of the ammonia molecule. So that's the ammonia gas molecule. The molecular formula for ammonia gas is NH3. Before doing the hybridization, let's make the Lewis structure of the NH3. So that's nitrogen over here, hydrogen, hydrogen, and the hydrogen. Now let's talk about the nitrogen first. What's the atomic number of nitrogen? That's 7. So the electronic configuration is 2, 5. That means nitrogen is having 5 electrons in its valence shell. So let's mark that 5 electrons around the nitrogen in the Lewis structure. So that's first electron, second electron, third electron, fourth electron, and the fifth electron. Now let's talk about the hydrogen. What's the atomic number of hydrogen? That's 1. So the configuration will be 1. That means hydrogen is having only 1 electron in its valence shell. So I'm going to mark 1 electron with each hydrogen. So that's the first hydrogen having 1 electron. That's the second hydrogen having 1 electron. And that's the third hydrogen having 1 electron. So what next gonna happen? Here hydrogen is going to make one covalent bond with nitrogen. So the first hydrogen is making first covalent bond with nitrogen. Now the second hydrogen will make second covalent bond with the nitrogen, and now the third hydrogen will make third covalent bond with the nitrogen. Now let's count the number of valence electron of hydrogen after the formation of bond with the nitrogen. So I'm counting for the first hydrogen. That's the first electron and the second electron. So that means first hydrogen has attained its duplet after the formation of single bond with nitrogen. Now let's talk about the second hydrogen. I'm counting its electron after the formation of bond. That's the first electron, nice, and second electron. That means second hydrogen has also attained the duplet of 2 electrons after the formation of bond with nitrogen. And same thing goes with the third hydrogen. Let's count its electron. That's the first electron and that's the second electron. That means third hydrogen has also attained duplet, that is 2 electron, after the formation of one bond with nitrogen. Now it's turn to count the number of electrons, the valence electrons of nitrogen after the formation of 3 bonds with 3 hydrogen. I'm counting the electrons for the nitrogen. That's first electron, second electron, third electron, fourth electron, fifth electron, sixth electron, seventh electron, and the eighth electron. So that means nitrogen has attained the octet, that is 8 electron in its valence shell after the formation of 3 bonds with 3 hydrogen atoms. Now, in the molecule of NH3, who is the central atom? Obviously it's nitrogen, because nitrogen is forming maximum number of bonds, that's 3 bonds. So here central atom in case of NH3 is nitrogen. So we are going to discuss about the hybridization of the nitrogen atom. So now nitrogen, what's the atomic number of nitrogen? That's 7. What will be the valence electronic configuration of nitrogen in terms of subshells and the orbitals? That will be 2s2, 2p3. So I'm making the orbital diagram in the form of box. That's 2s, and these are the 3 degenerate orbitals of the 2p. Now let's fill the electrons over here. The 2s is having 2 electrons. So that means in 2s we are going to make one electron with a spin of plus 1 by 2 and the second electron with a spin of minus 1 by 2. Now let's talk about the 2p subshell. The 2p subshell is having 3 electrons. The 2p subshell is having 3 orbitals also. So we are going to fill that 3 electrons according to the Hund's rule in the 3 orbitals of the 2p. So that's the first electron, second electron and the third electron. And Hund's rule states that firstly all the orbitals get 1 electron each, after then pairing will start. So here we were having the 3 electrons, so all the 3 electrons got equally distributed in the 3 orbitals of the 2p. So that's our ground state. So that's our ground state. Now let's come back to the Lewis structure. In the Lewis structure, nitrogen is forming 3 sigma bonds. Here nitrogen is forming 3 sigma bonds. That means we must have 3 orbitals containing 1 electron in case of nitrogen for the formation of 3 sigma bonds with the 3 hydrogen atoms. Because I have already told you, whenever the 2 atomic orbitals overlap to form the bonds, then 2 orbitals must have 1 electron each. So here the orbitals of nitrogen will overlap with the orbital of hydrogen for the formation of sigma bond. There are 3 sigma bonds. That means in case of nitrogen, we must have 3 different orbitals containing 1 electron each for the overlapping with the orbitals of 3 hydrogen, and the formation of sigma bond can take place. So let's check out the electronic configuration. This is 2s2 2p3. We are having 3 electrons in different orbitals. That's in 2p orbitals. One in 2px, another in 2py, and third in the 2pz. So in nitrogen, we are having 3 orbitals in 2p subshell containing 1 electron each. That means we are having 3 orbitals containing 1 electron each for the formation of 3 sigma bonds. So that means in this case, there will not be any excited state. Now, after that, there will be the intermixing of the atomic orbitals, and the intermixing orbitals will be one of the 2s orbital and another will be the 3 orbitals of 2p. One is the 2s and another will be the 3 orbitals of 2p. That means here 1s and 3p orbitals will intermix. In the previous lecture, I have told you that it's a very general rule. During the hybridization, the s orbital will always be involved. In all the hybridizations, we are having s orbital in the hybridization. So 1s and 3p orbitals will intermix, and that's called hybridization process. And that's called hybridization process. So there are total of 4 orbitals intermixing, the 1s and 3p. So we are going to have 4 new hybrid orbitals. We are going to have 4 new hybrid orbitals, and they all will be degenerate because of the equal energies of all the 4 hybrid orbitals. So these are the 4 hybrid orbitals with equal energies, also called degenerate orbitals. Now let's come back to the electronic configuration of nitrogen. We were having total of 5 electrons. The 2 electrons were in the 2s and 3 electrons were in the 2p. So we were having the total of 5 electrons. So now there will be redistribution of that 5 electrons in the hybrid orbitals. But firstly, which type of hybridization is this? Here the 1s and 3p orbitals are intermixing. So that means hybrid orbital will be sp3. We got the 4 new hybrid orbitals, and all the hybrid orbitals will be called as sp3 hybrid orbitals. The second orbital is also called sp3. The third orbital is also called sp3. The fourth orbital is also called sp3. And in case of sp3, we are having 25% s character and 75% p character per hybrid orbital. Per hybrid orbital. That means we are having 25% s character and 75% p character. That's why we got the hybrid orbital, and its name will be sp3 hybrid orbital. And we got total of 4 hybrid orbitals, and all the 4 hybrid orbitals will be named as sp3 hybrid orbitals. Now in these 4 sp3 hybrid orbitals, we have to redistribute these 5 electrons. So now let's redistribute the 5 electrons. So that's the first electron, second electron, third electron, fourth electron, and here's the fifth electron. I have followed the Hund's rule that firstly all the hybrid orbitals, as they are degenerate, they will all get 1 electron each. After that the pairing will start. So first hybrid orbital got 2 electrons. So I am writing one very important point at this side. Whenever the hybrid orbital is having 2 electrons, whenever the hybrid orbital is having 2 electrons, then that pair of 2 electrons will be regarded as lone pair of electrons. Lone pair of electrons, it's a very important point. So that means the 2 electrons in first sp3 hybrid orbital will be taken as the lone pair of electrons. Let's come back to the Lewis structure. Here the lone pair of electron on nitrogen atom is this one. So that's the lone pair of electrons. Now after that there is the formation of sigma bond between the sp3 hybrid orbitals and the s orbitals of the hydrogen. So let's talk about the hydrogen first. What's the atomic number of the hydrogen? That's 1. So what will be its configuration? That's 1s1. So we are having 3 hydrogen atoms. I'm taking first hydrogen atom over here. Its configuration is 1s1. Now this 1s1, this s orbital of hydrogen will have an head-on overlap with the sp3 hybrid orbital of the nitrogen to form the sigma bond, and this sigma bond will be obviously sp3s. Why so? Because this sigma bond has been formed by the head-on overlap of sp3 hybrid orbital of nitrogen with the s orbital of the hydrogen. Now let's talk about the second hydrogen. That's our second hydrogen. Its configuration is also 1s1. So this 1s1 orbital, s orbital of hydrogen, is going to have head-on overlap with the sp3 hybrid orbital of nitrogen to form the sigma bond. So we got the sigma bond again, and it will be sp3s again. Why so? Because this sigma bond has been formed by head-on overlap of sp3 hybrid orbital of nitrogen with the s orbital of the hydrogen. Now let's talk about the third hydrogen. So that's our third hydrogen. Its again configuration is 1s1. So that means here also the s orbital of third hydrogen is going to have head-on overlap with the sp3 hybrid orbital of nitrogen to form the sigma bond. So we got the third sigma bond again, which is sp3s. Why so? Because again this is the sigma bond that has been formed by head-on overlap of sp3 hybrid orbital of nitrogen with the s orbital of the hydrogen. So we got the three sigma bonds of same type, so the strength of these three sigma bonds will be equal. Now that's all about the hybridization, which came out to be sp3 for nitrogen in case of NH3 molecule. Now let's talk about the structure. Now I'm talking about the structure. In case of sp3 hybridization, the structure is taken to be tetrahedral, but in this case we are having one lone pair. Firstly, let's draw the structure of the NH3 molecule. So that's the nitrogen, and this is the sigma bond of first hydrogen, and this is the lone pair of electron which was present on nitrogen. Now let's assume this lone pair and this sigma bond is present on the screen. Now let me mark the type of sigma bond. This sigma bond is obviously sp3s, that has been formed by the head-on overlap of sp3 hybrid orbital of nitrogen with the s orbital of the hydrogen. Now this sigma bond and this lone pair are present on the screen. These are present on the screen. Now this is the wedge bond. This is the, I'm saying it's wedge bond to specify that this bond of nitrogen with hydrogen is coming out of the screen, and the another one is the dash bond. This is the dash bond that has been formed between the nitrogen and the hydrogen, and this dash bond stands for this is going inside the screen. So this wedge, dash and the simple line bond is just to specify, is just to make you all students understand this structure in 3 dimensions. Please try to understand this structure in 3 dimensions. The simple bond and the lone pair is present on the screen. The wedge bond is coming out of the screen, and dash bond is going inside the screen, right? And the another bonds also are of the same type, that's sigma sp3s, and the third one also is sigma sp3s, because these three bonds has been formed by head-on overlap of sp3 hybrid orbital of nitrogen with the s orbital of the hydrogen. So in this case, due to the presence of lone pair, we generally not take the lone pairs while naming the structure. So this is not taken to be tetrahedral geometry. This will be called as pyramidal geometry. So whenever a tetrahedral structure has one lone pair, it is named as pyramidal geometry. So in case of NH3, the structure will be called as pyramidal. Now in case of NH3, I'm specifying the bond angle. The bond angle is actually 107 degrees. The 107 degrees. You have to learn. Usually normal tetrahedral angle is 109 degrees and 28 minutes. But in this case, the bond angle will be decreased and it will be 107 degrees. The reason for this thing we will study in the Vesper theory. The valence shell electron pair repulsion theory will answer why this bond angle are getting small. So I hope you got this. So whenever the sp3 structure has one lone pair, then that tetrahedral geometry will be now named as pyramidal geometry. because we don't consider lone pairs while naming the structure of the any compound. So that's all for today. And now we are left with the energy points. Now let's talk about them. The energy points. Here we are having one endothermic process, and that was hybridization energy. So I'm writing here is the consumption of hybridization energy. Here is the consumption of hybridization energy. Now after that, when there is a formation of 3 sigma bonds, I'm writing during the formation of 3 new sigma bonds, comma, energy is always released. It's an exothermic process. The formation of bond is an exothermic process. The energy is released which compensates the hybridization energy in this case, which compensates or recovers the hybridization energy. That's why the formation of NH3 is practically possible. It's a practically feasible process because the hybridization energy is getting compensated by the energy released during the formation of 3 new sigma bonds. So that's all for today. I hope you all understood the hybridization of nitrogen in case of NH3. It's sp3 hybridization with one lone pair in the structure, and whenever there is a presence of one lone pair in the structure, then that sp3 structure will not be taken to be tetrahedral. It will be called as pyramidal. Please always keep this thing in mind. Whenever the tetrahedral geometry or sp3 hybridization we can say is having one lone pair, then that will be named as, that structure will be named as pyramidal but not the tetrahedral. So that's all for today. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.